Alrighty, today we are looking at logarithmic and exponential inequalities. We are going to be spending 2 days on this because this is kind of a sneak peek into some pre-cal material and it's a little tricky, so we're not expecting you to become experts on it in one sitting. So just a quick overview, our steps for these inequalities are to find the x-coordinates where the function has zeros, holes, or vertical asymptotes. These are what are going to become our critical points. And we're going to use those critical points to make a sign chart to determine the intervals where our function is positive or negative, depending on what the particular question is asking. Now, we are going to work backwards on this set of notes that I have given you because the first two are pretty tricky and I want to introduce you to some simpler ones first. So we are literally going to go to the second page and work the last two examples on that one first. So what we are looking at here on C is we want to know when these two logs subtracted from each other are greater than that one. So the first thing I'm going to do is condense this into a single log, and I firstly need to subtract this log on that side. So log base 2 of 56x minus log base 2 of 7 minus log base 2 of 5x plus 15 is going to be greater than 0. So I'm going to consolidate this using my log properties. Log base 2 of 56x over 7 times 5x plus 15. I can simplify this because 56 and 7 divide, so I've really got log base 2 of 8x over 5x plus 15, and I want to know when that's greater than 0. So my critical points again come from zeros / x-intercepts and vertical asymptotes, or where I would have a hole. So looking here, I'm going to have an x-intercept when my numerator is 0. So when 8x would be 0, well, if I divide both of those by 8, I get x is 0. There's one of my critical points. Another critical point is going to come from vertical asymptotes. Remember, we can't divide by 0, so what would cause 5x plus 15 to be 0? Well, if I subtract 15 and then divide, I get that x equals -3. There is my second critical point. The third critical point is going to be when I'm changing from negative to positive y values. If you think about your parent graph function for a log, right, we don't ever cross the y-axis because I can't take the log of a negative number, but we do have this point where we transition from negative y values to positive y values. And that happens where, for the parent function again, x is 1. The reason for that is when my inside function is greater than 1, remember your log means your base to this power equals a number. Well, when you have something to the 0 power, that is equal to 1. So when it becomes less than 1, we have a negative exponent. When it is greater than 1, we have a positive exponent. So our y coordinates are representing our exponents here. So I'm going to look at the boundary from when 8x over 5x plus 15 is equal to 1. That's going to be where I'm crossing from negative to positive y values. So to solve this for x, I would multiply it by my denominator. Then, of course, I'm going to combine like terms, divide, and I get that x equals 5. So there are the three critical points that are going to go on my number line. So I've got -3, 0, and 5. So what I'm going to do to fill in my sign chart is pick values that are before, after, or in between these critical points and determine if my graph is going to have a positive or negative output. So if this x value would give us positive or negative, or if it's undefined. So let's start with -3. If I pick a value smaller than -3, like say -4, for example, again, I'm looking at 8x over 5x plus 15. So let's say that I had -5. So 8 times -5 divided by 5 times -5 plus 15 gives me a positive number, and that number is greater than 1. So this graph here is going to be positive. Then I'm going to pick a number between -3 and 0, like 1. If I pick 1 here, I'm going to get 8 divided by 20. And that is And this did give me a positive number, but it's less than 1. So that tells me that my log is going to give me a negative output. And I do apologize, I kind of got ahead of myself. I did a positive 1 input, which falls between 0 and 5. So that tells me this interval is going to be negative. So let's backtrack to actually look at values between -3 and 0. I'm going to do -1 for that. So if I plugged in -1 here, that would be -8 divided by -5 plus 15 would be 10, and that's a negative value. Remember, I can't take logs of negatives, so my graph is going to be undefined at that interval. The last thing I'm going to look at is values bigger than 5, like say 6. So that would be 8 times 6 divided by 5 times 6 plus 15. Again, that is a positive number and it's greater than 1. So that tells me my y outputs are going to be positive. So the answer I'm looking for, again, I wanted to know when this was greater than 0, so that's going to be my positive intervals. That's going to be here when x is less than -3 and here when x is greater than 5. So those are the two parts of my answer. And then to graph that on the number line, you should be familiar with that. Open circle at -3, arrow going to the left. Open circle at 5, arrow going to the right. And there is my answer as an inequality. Okay, let's look at another example. Here on D, again, the first thing I need to do is get this as a single log. So I'm going to subtract to get log base 3 of 9x to the 4th minus 3 log base 3 of 3x. And I want to know when that is going to be greater than 0. So to consolidate this, I'm going to get log base 3 of 9x to the 4th over, that 3 means I'm raising both parts of this to the 3rd power, so that's going to be 27x cubed. This can simplify to give me log base 3 of x over 3. So I want to know when that is greater than 0, so I'm going to use my sign chart again. And remember, that comes at x-intercepts as well as vertical asymptotes and where we have that transition point from negative to positive outputs. So my denominator here will never be 0, so I don't have to worry about the vertical asymptotes. Values that are going to make my numerator 0 is when x is equal to 0, so there's one of my critical points. My other critical point is going to be when x over 3 is equal to 1. Again, that's going to be that transition from positive to negative values. So solving this for x, I get that x is equal to 3. So there is my second critical point. I'm only going to have 2 for this one, 0 and 3. And so again, what I'm going to be looking at is when I input values within these ranges, what happens with what's inside my log. So if I go with a value less than 0, like say -1, -1 over 3 is a negative number. I can't evaluate negative logs, so this is going to be undefined. Then I need to pick a number between 0 and 3, like 1, for example. Positive 1 over 3, 1/3, that is less than 1. It is positive, but it's less than 1. So I'm going to get a negative exponent there. Then for a number greater than 3, like say 4, again, it's positive, and it's a number greater than 1, so this is going to be my positive values. So again, I'm looking for when it's greater than 0, so that is going to be when x is greater than 3, and I can graph that here. Now, exponential inequalities are a little bit easier because I don't have to make a sign graph to complete them. So the trick here, though, is in order to compare them, I need them to have the same base. So starting on A here, I've got 2 and 4, so I need to rewrite this with a common base. 4 is the same thing as 2 squared. So if I have 4 to the x, that's equivalent to 2 squared to the x power. And if I use my exponent rules, this is the same thing as 2 to the 2x. So 2 to the 5x minus 3 is greater than 2 to the 2x. Now, to get my x's out of the exponents, I could take the log of both sides, which means I'm going to be left with 5x minus 3 and 2x. And those are going to have the same relationship as what was written above. So this is the inequality now that I'm going to solve for x. So you would just subtract your 2x, add 3, and 3x is going to be greater than 3. So after I divide, I get that x is greater than 1, and I can graph that on my number line. Okay, on B, these have the same base, but this one is not finished being written as an exponent. I need to make that happen. Remember, square root is really like raising something to the 1/2 power. So I'm going to use my power rule here, and I'm going to multiply. So this is 3 to the x plus 49 over 2 power, and that's going to be greater than 3 to the negative 3x. Again, if I took the log of both sides, what I would be left with are my two exponents, and they are going to maintain that same relationship. So to solve this for x, I could multiply both sides by 2. Then I can subtract x. And then I'm going to divide by negative 7, which means my inequality is going to change directions. And so my answer here is when x is greater than negative 7. Now we will get to the page of page 6, the first part of these notes really next time, because they are more tricky and I want you to have some time with the simpler ones first. Before you go, I know we kind of got sidetracked back to exponentials, but I do want to show you how this does play out in real life on a graph. So if I were to graph log base 2 of 8x over 5x plus 15, that would look like this. So as you can see, I do before negative 3 have those positive y values, and then I have a vertical asymptote here. My graph is undefined until 0. And then at 0, I'm starting off with negative y values until this switch point of 5. So those were my 3 critical points, negative 3, 0, and 5. And then looking at the other one, log of x over 3, similarly we can see our graph is undefined before 0. We're starting at negative y values and it crosses over to the positive at 3. So those were our two distinct points, again 0 and 3 there. So just so you can see that visually, if you need to graph these to help you complete your homework, that's perfectly fine. It is a paper assignment for this, and I want you to omit the very last question.